Talk about maintenance and repair. So no more numbers. No, it's only repair techniques. Well, as it is stated in the leaflet of the UIC, there are some principles and philosophy of what we understand as maintenance and repair, which is trying to keep structures in a serviceable condition to carry traffic. It's a very general definition, but it's the goal that we have to achieve doing all of this maintenance. And it is also stated in the UIC guide that any maintenance or rehabilitation intervention should maintain the structural integrity, not try to substitute or repose it, and be physically, chemically, and mechanically compatible. And this is really, really important because during the past years, all over Europe, we have been using techniques which were not compatible at all. Not only about the materials, but also about the construction details and the techniques. I have added this last sentence is that we have to try to be honest and to separate what we can call rehabilitation or refurbish, normal operation that we normally do because of durable problems, and what is repair or strengthening. And that's a really tough question, because for me repair is to try to recover the bearing capacity that the bridge used to have previous to the damage or to the defect. And to strengthening is that you have to increase the bearing capacity due to the increase of the loads or whatever. And this is a tough question because sometimes when we go to a bridge, we take advantage of some of the durability problems that are there. And by the way, we do these kind of things. No? We do a concrete saddle in the inner part because we think that it's going to be better. So this is, again, a Spanish bridge. So we used to do this in the 80s, in the 90s. No matter which is the problem, we are going to build a concrete in the surface of the bridge. And this is funny because, in my opinion, there was not clear at all which is rehabilitation, which is repair, and which is strengthening of a bridge. So the first question that we have to ask ourselves when we go to a bridge and we have to do this kind of maintenance operation is whether we are here, or there. So I will also want to spend a couple of minutes talking about the great difference that we have in new design and when we deal with existing structure. And this is, again, a very important issue. When we are doing new design, it's much more easier, for sure. I do both of them, and I can tell you this is far much more complicated. When you deal with new designs, first of all, in some way you have a safety framework that helps you. You have codes. And the only thing you have to do, well, the only thing, it's not that easy, but is try to have your bearing capacity log normal distribution on the right-hand side of the internal, well, the demanding forces that you have due to the loads, no? And normally the codes allow you to have this overlapping here, very little, which is the failure probability that we accept in our codes, no? But we know which is the context of our design. We have codes. We are very familiar with our structural types. We know them. We trust on our structural analysis and our models. So we treat with the ideal structural loads, not with defects. So this is completely different to this one. First of all, this is very similar to Adrian's figure that he showed yesterday. In this case, I have put another variable. Is here you have time. This is one very important thing that you don't have here. And here you have, on the one hand, the bearing capacity of the different elements, and this is the demanding, the forces that you have to deal due to the loads. So normally, you have a decrease on the bearing capacity due to the aging, to the traffic, whatever, no? But on the other hand, you always have an increase of the demand in solicitation, for sure. We will see that if you study the code loads, you always have an increase in this curve. So you have to be very careful in order not to get these two curves touched, no? So you have to implement this maintenance policy, but some people prefer to do very little repairs very often, and other more risky people, they go there and they play with the time, no? But at the end, everything is in here, no? You have to make decisions here. And the problem is these structures are real, no ideal, and they have their own history. And sometimes you do not know it. It's more or less hidden in the inside. Secondly, and this was also stated yesterday, we have lost many of the knowledge that they used to have. We are not very used to these materials. We are not very used to these construction procedures. We are not very used for the construction details and the way they understood the structures. There are no codes at all. Well, there are some codes for dealing with existing structure in Canada, and Sweden and Switzerland, I think. Be these, your codes have something, but it's of course not for masonry bridges. And the last one is there is a huge variety of materials and elements that we have in our bridges. No? The variability that we have in materials is incredible if you compare with post-tension concrete or steel, whatever you have here. So this is something that we have to bear in mind. We are in a very different scenario when we have to assess existing structure or to deal with existing structure. So again, this is more or less the general scheme of maintenance. We do some quickly and cyclic inspections every 4, 5, 6 years, depends on the country. No? In most of the countries, railways administration are doing this between 4 and 8 years. Even New Zealand do it every 8 and 10 years, something like that. It depends a lot, sometimes, on the age of the infrastructure, of course, and the structural types. And then, depending on the results of this stage, you go for a further inspection or studying. These are more complicated in order to know whether or not you have to do something or keep on going with the normal maintenance program. It is true that most of these structures are over 150 years old, and that's true. So they have lived more than it was expected for them. Now we design bridges for 100 years, and our bridges, they have been there for 150. And it is true also that we have damages or defects due to durability, at least, in almost 100 of them, 100% of them. Even the Swiss people, they have some durable problems. Not a lot, but even them, they have some problems here. So we are going to focus today in durability problems. Maybe they are not very urgent. They don't require urgent repairs, but they are, as I told you yesterday, they consume 80% of the budget, 70%, depends on the country, of the budget that we normally use for repair structure. And in this case, as I told you before, we have lost the construction technique, the knowledge, so we have been approximating to these structures in our own way. So let's talk about durability. We were talking about this yesterday. One thing are the symptoms, no? The defects and the damages. And the other thing is the processes, the illness, no? And this is like when you go to the doctor, no? It's not a question that he's going to cure a little pain that you have here. The problem is that he has to diagnose which is the real illness that you have. So in many cases, especially in durability problems, sometimes we only attend to the symptoms and we are not taking care of the real illness. So I will try to explain which are the main processes that we have in relation with durability, and also which are the variables that govern these processes. In order to identify which are the most common for each type of masonry, I know that here in UK, most of your bridges are brick masonry. But most of the problems are in the brick masonry. But all around Europe, we have a huge variety of different masonry in relation with the nature of rocks. No? We have sandstone, limestone. We have very different rocks. And all of them, the sensibility for these processes are different. So, and finally, we will try to identify the most appropriate techniques for these processes, not only for the damages, but for the processes. And this is important because, again, I think there has been a misunderstanding in the last 20 years that we think using modern and very rigid and strength material for repairing is good for masonry, and it's the other way around. We have to use material that do not change the perspire of the masonry, the rigid of the masonry, and things like that. So, well, we were talking about this figure yesterday. We have to quantify the durable actions. We have to study the material properties that are playing a role here in the different mechanisms of deterioration, of decay, of the durability process. So, in terms of actions, we have environmental, biological, and again the anthropological one, which are the worst one. These are the most common one, the climate one, temperature, water, wind, frost. But sometimes in big cities or in bridges where you are very near to industries, these problems can accelerate the processes. Into the biological one, we have bacterium and fungus, lichen, moss, and vegetation. We normally call of them vegetation problems, but there are some difference. Sometimes you really have to take rid of the bacterium if they are chemically aggressive, and sometimes you can leave the vegetation of the bridge. It's not necessary to take everything away. And that's another thing that maybe we are a bit aggressive with our intervention. And of course, we have to take care of the human action, which is accidents, previous reparations, over-exploitation of the structures, and things like that. This is some examples of this. So, I want to, for me it's quite important to convince you that these studies are not very difficult, they are not very costly, and you can do them very easily. So there is no reason not to do certain type of analysis when you reach to a bridge. This is the typical climatic study. You can do a general one using the data of rain, sun, days of frost very, very easily, and then you can go to the exact location of the bridge and try to guess if this is north-oriented or south-oriented, which is the part of the bridge that is more subjected to frost. So it's really, really easy to take into account these variables, this analysis in your analysis. And again, is not very easy, but it's affordable to know something about the materials that are being used in the structure. No? It's not a question of extracting cores and breaking it in order to have the compression strength. It's a question of know which is the type, the nature of the masonry. No? If you have a granite, you have a slate, sandstone, limestone. The only thing you have to do is look through the trace of the railway. You can see the rocks over there. Even if you locate the bridges in a geological drawing, you more or less can guess which is the material that they have used to build the bridge. All of these are quarries, all quarries that they are near the trace. So you can go to the quarries and try to guess which are more or less the masonry that they have been. This is a Spanish example, well, I imagine that here is more or less the similar. So it is not very difficult to have a qualitative information of which are the materials that you will have in the bridge. Apart from that, normally lines were built by the direction of one engineer, so you can find the signature of the same engineer in various bridges with the same materials, with the same structural times, geometrical ratio. So gathering this information for railway lines is not that difficult. However, you can do after some specific studies. You can do, well, microscopy, we will have a look of all of these studies. You can do some aging acceleration cycles. You put these pieces of masonry in a place and you simulate 100, 1,000 cycles of freeze-thaw attack or salt attack. No? But you can guess which are the salt contents that you have in the bridge, in the pieces, in masonry. All of these tests are really, really cheap. And it is quite easy to get a little piece of masonry, put it on your pocket, and go to the laboratory. You don't have to go with big machines. And it is true. I mean, and they are quite quickly to perform. Even you can try, but this is a tricky question, you can try to link durable variables with mechanical, for example, with mechanical variables. For example, you can try to link porosity with compression strength. No? That's one thing that we have tried to do. It's quite complicated, but so this kind of study can help you to know more information about materials. We are not looking for mechanical parameters. We are looking for those parameters that govern the durability processes. No? So we have petrography, X-ray diffraction, electron microscopy, X-ray fluorescence, analysis of the salt. All of these, the only thing you need is a little piece of your, and go to a laboratory. I mean, you can have this in 1 week for 500 euros. It's not something like that. These others are much more complicated, okay? The hydric test is you try to guess which is the absorption and desorption of the pores that you have in your rock. All of these tests are related to quantify the sensibility to the salt attack and the freeze-thaw attack. So are really important. These are more expensive, but for example, you can do them to characterize not only one bridge, but some of them that were built in the same moment. And also mechanical porosity, spring set. So there are quite a lot. All of them were created, I think, and they were developed for heritage, not for our bridges. But I think we can take advantage of all of this knowledge and apply it to our bridges. They were developed for cathedrals, something, well, more representative elements, but we can take advantage of them. And as I told you, they are not very difficult, they are not very expensive, and they are quite quickly. So for example, this is the salt content in a sample. You have chlor, potassium, calcium, you know, here. And the other thing is, after you have to guess where these salts come from. It is from the proper rock, or it's from the soil, it's from the water. So the origin of these salts, again, is quite important, no? And this is try to guess which is the amount of cement that we have in a limestone, things like that. These are the hydric tests. This is the absorption cycle for, this is quite important. This is the other, the desorption test. We normally do this. It's quite simple to do. This is the humidity map and also the map, salt maps. Now here it used to be a drainage, so we have water all over it. So we normally do this before and after a reparation in order to know if we have been successful during the reparation. So the only thing you need is a protimeter, which is the only thing that it measures the conductancy. So Depending on the level of humidity, it gives you values. It is very easy to have these kind of maps. So after quantifying the loads and after trying to characterize which are the properties of materials that govern these processes, we will go on trying to identify which are the most common deterioration process that we have in masonry. We have salt attack, we have freeze-thaw attack, which we have, this is really important, the change of the normal transpiration condition in masonry. We have dissolution of calcium carbonate, we have defect due to the run of water, the cementation of the limestone, and previous reparation, which is encompass all of them. So for example, in the salt attack, the problem is trying to guess where is the origin of the humidity. It's an upward capillarity, it's lateral capillary from bad drainage field, it's percolation or infiltration from the track. And we also have to more or less guess which is the origin of the salts. This is the presence of organic material in the environment, geological facts, constructive facts, aggregate from Portland cements, accidental facts. No? So this is more or less when you go to the inspection, well, what you try to guess. Is the water coming from capillarity, from both sides, or from percolation of the water? No? So, which are the damages or the defects that we can be associated to these processes? No? So at the beginning, we used to have all of these names, but we call them superficial deteriorations because these are very, very specific names for very little differences in the symptoms. So we decided that if I cannot see the difference, normal inspectors are not going to see the difference. No? That's another thing that you have to be aware. These are things, no, when you put something in a catalog or in a technical document, it has to be clear for someone that through visual inspection, they can make a difference between one defect and another one. So at the beginning, we were trying to be very, very accurate in vesiculation, deplacation, aerodization, exfoliation, but it's too much. No? So all of these, no, this is a sandstone in the south of Spain. This is deplacation, this is vesiculation, this is exfoliation. So all of these are damage that are related, or defects that are related with the salt attack. So the structural incident is not a lot. It's maybe you have a loss of section in a structural element, and of course you normally have loss of material joints. No? This is in some ways the same, the freeze-thaw attack. The problem is these salts in general, when they crystallize inside the pore, if the pore of the masonry is sensible, it grows and the pore is subjected to this mechanical action and it breaks, no? In this way. So it's a mechanical action. This problem, the salt attack, and the freeze-thaw attack, they are not a chemical problem, it's a mechanical problem. So what you have to do, the areas of direct runoff, the capillarity, humidity, infiltration through the track road, the damages, again, the escamation, the placation, the microcracking, and the structural incidents, loss of material joint, and also loss of section. These are, again, they are very similar processes. One is related to water, normal water, and the other one is water with salts inside. This is one of the worst, and is because of us, the humans, no? And this is related to previous reparations, and this is quite dangerous, no? Because as I told you, many years ago, we thought that instead of putting a lime mortar in the joints, it was better for the bridge to put a very rigid cement mortar, no? So what we have done is, instead of having the water coming out through the joints, the joints are the sacrificial elements of masonry. You have to repoint a bridge every 30, 40 years, is what you normally have to do, because you know that water is going to go outside from the joint. So if you put here a cement mortar, what you are doing, or a coat, even worse, or a plaster, what you are doing is you are changing. Now this is the rigid element, this is the piece, and this is going to be the joint. So this is what you have, you see? It's like a panel structure. So you have the joints perfectly there, and the elements, the pieces are completely destroyed. So you have to be really careful with choosing the material for the pointing. It's not that easy, because if you choose a very, very soft lime, it's going to last only 5 years. So you have to be careful. You have to find the equilibrium between not changing the transpiration properties of masonry in general, but putting something that is going to last at least 5, 10, 20 years. No? That's why it's important to quantify in some way the properties that you have in the rocks. No? This is our example. Here you can look it. This is a mess. I mean, this is quite common. Eh? Instead of putting the material inside the joint, they put the material outside the joint. So this is one of the things that we have to be careful. This is another problem that we have with some of our limestones. No? We have the dissolution of the calcic carbonate. No? When you have this kind of crust here, maybe they are because you have the water wash all of the cement that you have in the infill, but also can be because it's dissolving the calcic carbonate that is inside the rock. And in that sense, it's dangerous, because if you hammer the piece, it sounds sound because it's rigid in the outer part, in the outside, but inside it's only sand. No? So you have to be careful. If you lose this rigid cover, the problem is in the inside. So, well, again, the water is always the problem. We have to stop the water. The water is the responsible of 90% of the durable problems that we have in our bridges. Well, here is more or less what I was talking. You have the humidity, and you have these stalactites and stalagmites in the inner part. This is the reaction that you normally have with the limestones, and this is the appearance. This is not very important by itself, but it's telling you that something is happening in the inside. Again, damages due to the run of water. These are some examples. No? They are very common in all of the bridges. So we have to take care of these elements. I don't know how to say in English, the imposta, we call it in Spain. No? These elements, the wrinkles, they are not only compositive architectonic elements, they play a role in the bridge. So if you don't have them, like here, you are going to have a problem of water, or like here. No? So you have to keep on replacing these elements. No? The impact is general stains or spot, fungus colony, well, manganese, depending on the other elements that you may have on the bridge. And it doesn't have, again, a very important structural incidence, but it can evolve in a way that you require a most traumatic intervention in the future. Again, this is one of the hidden problems that we have with the limestones. Is the dissolution of the cement, which is here it's in Spanish, sorry, it's in orange. This is the normal structure for a limestone. If you have water inside, it dissolves and it concentrated again in the outer part. No? Here you have very little cement inside the rock. So again, if you get one of these rocks and you hammer it, it sounds strong. But in the inside, it's only sand again. So you have to be careful. This was the crown ashlar of a bridge. Look, the shape is like this. Instead of being like that, no, with this shape, it's completely rounded. No, these things that can happen, no, because sometimes defects, they are not only because of durable problems, they are not only caused by strength problems. They are a mix of both of them. No? So this can happen in some of the bridges. You have the cementation, you lose the shape of the ashlar, it goes down, and then you have a compression more in the inner part, and it breaks. No? So we have plenty of these problems with our limestones. And again, we were talking about this before, previous reparation, cement mortars, look here. This is a very good example. No? And the problem of this, you cannot repair this. This is a no way, no go back solution. In order to repair this, you have to break everything. So this is a multi-ring bridge, and this is the spandrels. Here again, look, all of these joints with cement mortar.
What's the reason? What's the cause?
Here, because they have used cement mortar to repoint the. This is what very used in the 70s and 80s in Spain. Now it's completely forbidden, I might say. So it's completely forbidden to use cement mortar in our bridges since 19s or 95 or something like that. But it used to be a very common practice to use this kind of modern material. Of course, we have to use modern materials, but not in that sense, with some more intelligence. No, it's not the better properties the material have, the better is for the bridge. It's not like that. No, you have to search for life cycle and compatibility. So I will end with some recommendations for the techniques. No, so we will talk about what we call, or what we could be, the normal conservation and maintenance activities that we normally do in our bridges. Cleaning, soluble salt extraction, well, this is not very common, but it's very cheap again, and I would recommend you to do it. Element reconstruction, replacement of pieces, pointing, injection of crush, consolidation. This is an important issue, and also the hydrofugation of certain elements. So all of these techniques are associated with durability damages, almost present in all the bridges, and they do not imply retrofitting for sure. Not very complicated, but they are really, really very frequent. So we should know how to do them. Cleaning, no? And this is, again, an important issue. Do we have to clean our bridges? No? And I think, at least what I have seen, is that we have maybe a very hygienical mentality. No? Sometimes we clean everything, and there is no need to do that. Sometimes you have to clean in order to see things. In that case, is interesting. But sometimes you clean as much that after you are losing the patina, which is really important for the bridge. But we have to know which of these stains, crusts, are really important for the durability of the bridge. For example, black stains, sometimes they are organic, so they are not important. Sometimes are because of petrol or other issues. In that case, you should get rid of them. The film or spotted again. No? Sometimes you have to take rid of the fungus because they are chemically aggressive. Other times, no. And here is we will talk about this real necessity of cleaning and which are the techniques that we are going to use. Because we normally use these ones, the industrial ones, sandblasting and things like that, and sometimes they're very harmful for the bridge. So we should try to introduce, in some cases, the heritage techniques that are available in the market, and they are much better sometimes. So how we select the good criteria for the suitable technique? We have to look at the surroundings of the structure, especially the medioambiental issues. No? You cannot, for example, we normally, instead of using sand for the cleaning, sandblasting, we use, it is called silicato etilo. This is a little round balls coming from the industry of steel industry. And the point is that they are round, so they do not have this acicular form of sand, so it doesn't scratch the masonry. It only takes out the rubbish by the impact, no? But on the other hand, they are very they are not allowed in special places. You have to take all of them after, no? So So you have to look at, to take a look for the surroundings of the structure, the typological characteristic of the elements, the materials. It's not the same sandblasting a granite, which is indestructible. Well, Bill says that the granite is not indestructible, but it's almost indestructible and chemically inert than, for example, sandblasting masonry, brick masonry. So you also have to have in mind the historical heritage value of the structure and the final aspect that you want to achieve. Because once you clean a lot the bridge, then you have to have an integral repair of the bridge. Otherwise, you're going to have the bridge like in different colors. Right? That's another thing that you have to bear in mind when you start cleaning something. So there are some chemical techniques for cleaning. All of them are a bit complicated to use. The only one I really recommend is this one. It's the technique based on the formula AB. This is an organic chemical component. It's not very aggressive, and for example, for graffitis and special stains, it can make a difference. No? The technique based on acids and strong bases are really dangerous because you can clean the masonry, but maybe you can kill the masonry as well. So these are quite difficult to apply. This one is softer, and I really recommend it. We also have some techniques based in special clays and biological adhesive strip, but they are very, very well. I think they are only for heritage structures. And the physical techniques, which are the most common ones, this is the most common one to project an abrasive, but you have to take care of which abrasive are you going to project, because you can, again, harm the structure. You have laser beam, ultrasounds. These are very related with heritage structures. We have been used this one, nebulized water and pressure jet. These are most common, like this one that you see here. And which are our specific recommendation for masonry art bridges? The cleaning operation must be focused only on the elimination of salts and black crust, okay? You do not have to clean everything in a bridge. Material should prevail over the aesthetics. So in order to clean anything, if you have to break the material, please leave the material, and maybe you will not have a uniform layout, but it is better to leave the material as is it. Acid and strong bases are not of general use. Dust, black stain, and crust are more general problems. Fungus and organic alteration can be cleaned by only brushing with some water with formol. No? So cleaning is an issue. It's not an easy task. It's not only things that you put in your project or in your design project, clean the bridge. You have to specify, in my opinion, which is the part that you are going to clean and how are you going to clean the bridge. Well, projecting of abrasive aggregate can be harmful. Brick and sandstone masonry for soft masonry. Be careful with the usage of chemical agents. And if you are going to use humid techniques, water or something like that, you have to know the masonry answer to the water. No? Okay, let's move to the other one, which is the salt extraction, the element reconstruction, the replacement of pieces, pointing, injection, hydrofugation, and consolidation. All of these techniques are related to salt attack, frost and frost cycle, aging due to running of superficial water, internal filtration and percolation of water, and previous intervention to all of these damages. So salt extraction, again, maybe it sounds a bit weird to do that in a masonry art bridge, but again, sometimes it's not very expensive and it's quite easy to do. The only thing you have to do is to put an inner material, can be cellulose, paper, no? with some absorbent properties, with water. And you put it on the layout of the element, and you wait until it is dry. And when it's dry, you take rid of it. That's all. Then you have to do it maybe 2, 3, 4 times until all the salts come out. Maybe this is a problem. You have to do it several times, but it can be really useful if you have really problems with salts, no? Element reconstruction, again, here you have to select very carefully the compatible materials, no? We normally use different mortar for the piece, of course, than the one used in the repointing. The one used in the pointing has to be softer. I really recommend to do hydraulic limes, and of course, not cement. You have to prepare the surfaces, cleaning and salt extraction, and you have to reconstruct a lot. You have to, in order to have cohesion, you have to add some epoxy or stainless steel sticks, like this, previous to the reconstruction of the elements in the several coats, no? We normally do that not because of the strength purpose. We do not want to recover the bearing capacity of the element. The only thing that we want is to recover the layout, no? I do not want to have water going inside this element again, because it's going to accelerate the problems. The purpose of doing this element reconstruction is to recover the shape of the arch, but not in order to obtain more strength capacity. I'm quite sure that this is not going to carry loads in the future, no? It's to stop the problem in certain areas. It's the same with the replacement of pieces, no? So you have to prepare the thing, and it's not very common for a strength proposer, and you have to again choose the material. And this, sometimes it is better, it's quite difficult to know where you have to do the reconstruction or when it's better to put another piece, no? Sometimes you have to again think about it. Pointing is a very easy task, but normally people do it very bad. And I cannot understand why. I mean, you put in your design project all of the specification, the material, the previous task, and they, instead of putting the pointing here, they put it there. You see it? And this is crucial. I mean, you have to have the material inside, not the outside, no? So, again, it's a very common task. You have to prepare the joint to select an appropriate dosage, confer some humidity to the surface, and fill and seal in the joints. You have to be careful for the mortar because of the porosity, stiffness, and strength. And you have to take a look to the climate condition during the operations. Injections. Injection, more dealing with sealing cracks, not injecting cracks, because in masonry we are not in concrete, no? We do not want maybe to penetrate in a width of 0.3 millimeters, 2 meters, no? It's just sealing the huge crack and the hollows, for example, for consolidating the backfill. So we have to prepare the cracks, cleaning and drilling. We have to bear in mind which is the sequence, pressure, and volume of injection that we are going to have in the injection plan. You have to have an injection plan, because in masonry, maybe you are thinking of injecting 200 liters and you end injecting 500. It's like that. I mean, so in my opinion, if you are injecting 30–40% more than the amount that you have previously stated, you have to stop, because maybe you are injecting the embankment or whatever, no? So this is not a... You have to write previous to the injection what you are going to inject, which is the sequence, which is the volume, the location of the mouthpieces. So you have to... Maybe you have to readapt that on site, but you have to think about how are you going to do this, which is going to be the pressure, no? For the pumping. Is 1 atmosphere, 2, 3, whatever. Consolidation, yes. We used not to do this a lot because it was very expensive, no? Consolidation is a technique where you inject in the rocks some kind of a cement. You can penetrate at least 4 or 5 centimeters. You do it with an injection, with a, I don't know how to say, ¿cómo se dice jeringa? Syringe. So it's a very specific technique, But nowadays it's getting more and more cheap. No? So sometimes if you want to consolidate the layout of your masonry, you can do this technique. It penetrates at least 4 or 5 centimeters and improves the cohesion in masonry. No? You have to prepare the surface, and the application of the products, well, this is not bad. This is for hydrofugation, sorry. It's with an injection gadget. So it's not very frequent. It depends on the level of penetration, the climate conditions, and sometimes they are chemical products. So you have to be careful about the secondary reaction and effects, because maybe you can have a yellow color all around the bridge or something like that. No? So it's I think it's a very interesting technique where when you have a very aggressive climate action, but on the other hand, you need to test the product on site, and you have to do a lot of pre-arrangement prior to the execution. And finally, the hydrofugation. This is quite common. I don't know if you do it here. We normally put this kind of products in the elements that are more subjected to the run out of water. No? It's like your dockers, no? Your trousers. The water run out very quickly. The problem with this product is the life cycle of them. If maybe the industry is going to tell you this is going to last for more than 20 years, but I think that's not true. I mean, the life expectancy of this product is about 15 years or something like that, 10, 50, depends. But it gives you a lot of, well, it improves a lot the life of this structure. And there's another secondary but very useful advantage of this product is that you put, for example, hydrofugation in an element. If you have after graffitis, you can take them out only with water, because this product go inside the pore, so the paintings do not stick to the real rock. So it is much more easy to take them out. No? So for urban structures, I will apply hydrofugation in most of the elements in order not only to protect the masonry, but also to have, for cleaning the graffitis. And that's all. Thank you.